The final type of reaction I would like to mention is oxidation reduction of alcohols. Before we begin, we need to understand what is oxidation or reduction reaction first. For inorganic compounds, it is very obvious because you can look easily at the oxidation state of your, for example, the metals. For example, from chromium 3+, if you convert it into chromium 6+, you lose 3 electrons. So it is loss of electrons of a species. So chromium 3+ lost its 3 electrons to become chromium 6+. So this is the oxidation. But for the reduction, it is the gain of electrons. For example, here, chromium 6+ can gain 3 electrons to become chromium 3+, for example. But for organic compounds, this is a bit more difficult to understand. So you need to look at the oxidation level of carbon first. So for example, if you look at the alcohol, for this carbon here, if you look at the oxidation state, you need to compare with the nearby atoms around it. For the hydrogen group, it has lower En than the carbon. So this is +1. This hydrogen is also +1. The methyl group has the same electronegativity as the carbon, so this is 0. Okay. For oxygen, it has higher electronegativity than the carbon, and the hydroxyl group is therefore -1. So in total, if you want to balance the charge, this carbon here must be -1 oxidation level. If you convert this into an alkane, for example, the left-hand side carbon here, if you look at the oxidation level, this is +1, +1, +1, and 0. Therefore, this carbon is -3 oxidation state. And in order to convert from alcohol to alkane, you gain 2 electrons. Therefore, this is the reduction process. Okay. But if you change alcohol into, for example, alkyl halide, so this is +1, +1, 0, and chloride has higher En than carbon, so this is -1, and therefore the carbon is -1 oxidation level. So this is not the reduction, not the redox process. This is not oxidation, not reduction, just a simple reaction that we mentioned so far. Like in the first 2 clips, when alcohol reacts as a nucleophile or electrophile, they do not change oxidation level, so those are not oxidation or reduction. Okay. For example, the protonation of alcohol, you will generate, so this is 0, this is +1, +1, and again oxygen is -1. So in total it stay as -1 here. So this is also not oxidation or reduction, just a simple, simple reaction, not redox reaction. But if you change from alcohols to aldehyde, in this case, this hydrogen, so if you consider this carbon, this hydrogen is +1, this carbon is 0. For this oxygen, it forms double bond to the carbon, so this is -2. So overall, this carbon is +1. So in order to change from alcohols to aldehyde, this is the oxidation, because the carbon need to lose 2 electrons. And if you look at this carboxylic acid, this carbon has 3 nearby groups. For this carbon is 0. This oxygen is -2, and this oxygen forms single bond, so it's -1. So in total, this is +3 oxidation state. And again, in order to change from alcohols to carboxylic acid, you need to oxidize it. So this is another oxidation. Okay. If you look at this diagram, starting from an alkane, you need to oxidize one step to become an alcohol, and the primary alcohols can oxidize again to form an aldehyde, and the aldehyde can oxidize again to form carboxylic acid. However, if you now have two substituents near at the carbon, starting from alkane, you can oxidize one time to form secondary alcohol, and you can oxidize again to form the ketone. But from here, you cannot oxidize it further because you are blocked by two alkyl groups. So the ketone is now the maximum oxidation level. And lastly, if you start from alkane with three substituents, you can oxidize one time to tertiary alcohols, and now all of the groups are blocked by alkyl groups, so you cannot oxidize even any further. Okay, and from top you can reduce back. So for example, carboxylic acid can be reduced to aldehyde, to alcohols, and to alkane using different types of reactions. Okay, but you need to understand that there are some maximum oxidation level. For example, the carboxylic acid, you cannot oxidize it further. Ketones, you cannot oxidize it further. And tertiary alcohols, you cannot oxidize it further because there are some blocking groups that you cannot change it into oxygens. For the oxidation of secondary alcohols, we know that it can oxidize into ketone, which is the maximum oxidation level of this secondary alcohols. You can use a strong oxidant, which is sodium dichromate. The active species here is the dichromate anion, so which has, if you try to figure out the oxidation level, this chromium is 6+, right, which has orange color. When it oxidizes, it will become chromium 4+, which is greenish blue. So you can look at the color of the reaction, whether it proceeds already or not, at the color of the reaction. For example, cyclohexanol, here is the secondary alcohols. It can transform into the ketone by using sodium dichromate to form cyclohexanone. Okay. For the mechanisms, we know that the oxygen of alcohol is slightly nucleophilic, and the chromium of the chromic acid is very, very electrophilic because it connects to 4 other oxygens which are electron withdrawing. And in the condition, we also have the proton, which will protonate one of the hydroxyl groups to make it a good leaving group. Okay, so from here, you can use the lone pair of alcohols to attack the chromium, kicking out the leaving group. And from here, if you remove the proton and stuff like that, you can form the chromate ester, which is now you have a good leaving group here. Okay, and you have the acidic proton here. So from here, you can use some nucleophile, for example, water, to abstract this proton, kicking electrons to this oxygen and kick out this whole leaving group, the chromium 6 leaving group. And then if you draw these mechanisms, you will form a ketone with the chromium 4 species. So it changed from chromium 6 with orange color to chromium 4 with a greenish color. You can also use other strong oxidizing agents, for example, copper oxide, Collins reagents, Jones reagents, potassium permanganate, nitric acid, and sodium hypochlorite. So these reagents has the same thing in common, which is the high oxidation level, because you can use these as a strong oxidizing agent, converting into so you can use this to accept electron from alcohols to form ketone. For example, permanganate, this is +7 at the manganese, and you can use it to oxidize alcohols to form manganese dioxide, which is +4. Or sodium hypochlorite, this NaOCl has the OCl- species. So this chlorine is +1 in oxidation level. Okay, so this can be used as the oxidant, converting cyclohexanol into cyclohexanone, and itself becomes -1 oxidation level. For the primary alcohols, there are two options. The first one is the oxidation one time to aldehyde, and it can oxidize further to carboxylic acids. So if you do not control and you use a strong oxidant, it will go straight from primary alcohols to carboxylic acid. For example, if you use a strong oxidant like dichromate here, this is a strong oxidant, and you will not stop at aldehyde. It will go straight to carboxylic acids. So it is too strong to stop at the aldehyde, but if you want to get the carboxylic acid, this is a great way to convert alcohols into carboxylic acids. But what if you want to stop at an aldehyde? In order to understand how to stop at the aldehyde, you need to understand first how does carboxylic acid is formed under these conditions. So with dichromate, it is in equilibrium with the chromic acid, and under acidic conditions you can protonate one of the hydroxyl group to becomes a good leaving group here, and the chromium here is electrophilic, and therefore the oxygen can attack this chromium, kicking out water and lose the proton in order to form this species, which you can eliminate the proton kicking out this chromium as a chromium 4 species, and then you get the aldehyde. From here, it doesn't stop here. Aldehyde is electrophilic, and later on I will show you that aldehyde is in equilibrium with the hydrated species by reaction with water. Okay, so the water can attack the aldehyde in the presence of acid. Okay, from here you will generate this species after removal of proton. So this species is also an alcohol. It will attack the chromic acid again, kicking out water, and then you will form similar species to the first one, and then after that you can kick out the chromate species by the similar mechanism, right? And when you remove the proton like this, at the end you will generate carboxylic acid, kicking out the chromium 4. So you can see that oxidizing alcohols into carboxylic acid aldehyde occurs in the reaction, but because the aldehyde can react with water to form the alcohols again, therefore it will oxidize further to carboxylic acid. So if you want to stop at the aldehyde, one way to stop it is to use the condition that doesn't have water in the reaction, so it stops at the aldehyde, right? There are a few reagents for transformation of primary alcohols into aldehyde. One of them is pyridinium chlorochromate, or PCC. Okay, this consists of the chlorochromate species, which is chromium 6. If you draw the structure, it is chromium with 2 double bond oxygens, oxygen minus, and chloride here. So this chlorine is a good leaving group that when your alcohols attacks, this can kick out the chloride, and then you can it can undergo the same usual mechanisms where you can remove the proton here, feeding electrons to here, and kicks out the chromium 4 species. And then here, because the pyridinium chlorochromate is like soluble in nonpolar solvents, so you don't need to use water in this case. Therefore, you won't have water to transform aldehyde into the diol here. Therefore, there is no overoxidation, and you can stop at the aldehyde level. For example, heptanol can react with PCC to form heptanal in 78% yield. So far, we mentioned about the oxidation of alcohols into aldehydes, ketones, and carboxylic acids. If we talk about the reduction of alcohols, the product would be an alkane. However, this kind of reduction is very rare. This is not common at all. Not many people want to reduce alcohols into alkane, and it is very rare. If you want to really make an alkane from alcohols, you probably need to use two-step process. For example, you can use acid and heat to eliminate water to form an alkene, and from here you can use hydrogenating agents like hydrogen gas with platinum catalyst to introduce the hydrogens from alkenes to alkane. The other way is by using alcohols with tosyl chloride to transform the alcohols into a good leaving group. And from here, you can use some hydrogen nucleophilic species, for example, lithium anhydride. This is source of H-, which I will introduce to you again later on. But you can think of it as a nucleophilic hydride source that can use to attack and kick out the tosylate group, and therefore you can replace the tosylate group with hydrogen, and at the end you change from alcohols into alkane. But this kind of transformation is quite unusual and not very common. So to sum up the reaction of alcohols, first, the oxygen can act as a nucleophile to react with electrophile to form RO electrophile. Okay, but you can also increase the nucleophilicity of the oxygen by reaction with a base that can remove the proton and form the alkoxide with even more nucleophilicity. You can also activate the hydroxyl groups to become a better leaving groups by reaction with acid or reaction with some other sorts of electrophile to make them a leaving group, and from here you can use a nucleophile to attack the carbon and then replace those groups with the nucleophile. Another mode of action is that you can oxidize the alcohols to form ketones, aldehydes, or carboxylic acid, depending on which type of alcohols and the reagent that you choose. Okay, so that's all of the reaction of alcohols. You can try to attempt all of these homeworks, and again, please draw it in maybe an A4 paper or in your iPad, and then you can save it in a PDF. Please only save it in a single file and hand it in the Blackboard system. For homework 1, you are going to rank the boiling point solubility and acidity of the alcohols. Next, you are going to predict the product, and please draw the mechanism of each step for these reactions. In this case, please try to fill the boxes, and if you have time and you want to practice, you can try to draw the mechanism of each step as well. Same for this one. If we mimic the synthesis of fluorescence nanoparticle, where you have your nanoparticles with an alkene at the surface, and you want to attach a fluorescence probe onto the surface of the nanoparticle through this scheme, try to predict the structure of the product in each step. And if you want to practice, you can try to draw the mechanism of each step as well.